Sachs & Associates offers training in C and C++ for companies all over the world. Got quite a bit to talk about here, so let's go ahead and dive in. All right, so we're going to be talking about move semantics today, but why do you care about this? Well, copying, not moving, but copying specifically, is a pretty common operation to perform in C++, but there are a number of objects, containers for example, that are expensive to copy under most circumstances. And so move semantics, by implementing these for your types, you can sometimes turn certain what might have been an expensive copy operation into a relatively cheap move operation. Now, just implementing move semantics will do part of that for you because the compiler can recognize some situations where a copy operation can be automatically turned into a move operation safely. But there are other situations where you need to give the compiler some kind of extra hint to let it know a move is safe in this situation, even though it might not be obvious there. Unfortunately, sometimes providing that hint when it's not necessary can actually send the compiler down a slightly less optimal road than it might have gone down if you just left it to handle the situation on its own. And so that's part of what I want to address here is having a full understanding of move semantics, I think, will help you recognize the times when you want to provide that explicit hint and when you want to just leave it up to the compiler. Now, this is a little bit tricky because the traditional examples of move semantics, sort of the classic situations where you really wanted to be able to take advantage of it, there have been other advances in the language that have happened over time that mean that some of the things that historically we wanted a move operation for have actually now been solved in other ways through copy elision or move elision, as it's sometimes called. C++17 in particular added some requirements where copies have to be elided in certain situations. So I'm going to start out by describing this from a theoretical perspective in terms of how things would work in historical versions of C++, and then I'll describe a little bit later on how things work in the modern world where if you're compiling it with a more recent version of C++ and some of these operations actually are elided. So the idea of moving a value from one object into another is something that we see in a few different places in C++. For example, the swap function template is something that does basically that kind of thing. I mean, if you were writing this code in C++03, this is what the swap function would have looked like before C++ added move semantics. And I'm using, this is fully meant to be C++03 code. Each line here is really performing a copy operation in terms of what it's actually doing. But functionally, what we really want to do is take the value that's in X and move it over to Y, and take the value that's in Y and move it over to X. Now, if we're talking about built-in types, scalar types, using the copy to do that is pretty much the best that we're going to do. Ints don't have any internal structure or anything like that that makes copying different from moving. But for class types, the kinds of things that generally have expensive copy constructors and copy assignment operators, the swap function can be pretty inefficient, as I just showed you. So here, for example, let's take a look at just a basic implementation of a string type class that uses a dynamically allocated character array here. So this is the class myString, and this is a fairly typical string class using a dynamically allocated array of characters that you'd expect to see in a lot of basic applications if we didn't have the stood string class to use. The stood string class is significantly more complicated than this. It employs a number of optimizations that are meant to help in a variety of situations. But this is the kind of thing that you might write by hand. I've also, if I were writing this today, I would probably make use of the smart pointer types. But the thing is, for the purposes of this talk, the smart pointer types already have move-semantics implemented. So if I tried to use one of those, that would sort of defeat the purpose of the talk in some regards. So I've omitted that. I've also left out certain helpful qualifiers like const expr or no discard here, so as not to clutter up the slides too much. But if I were writing this code for production, I would absolutely take advantage of qualifiers like const expr to make this more efficient, more usable at compile time. So here is the constructor for the myString class. It goes ahead and it stores the length of the string in this stored length field. And then it has the actual stir field that has a dynamically allocated array of characters where it stores the spelling of the string in a null terminated fashion. If you were drawing it up as a picture, creating the string hello for S1 would look something like this. And the destructor simply goes ahead and deletes the dynamically allocated character array. Again, I don't think this should hold any surprises for people. The copy constructor, in order for this string type to work correctly in the way that we probably would anticipate, if we want to create an actual copy of this string, and here I'm not talking about I want to move it, I really am talking about I want to copy this string, get another string that has the same value. I'd want to make sure that that copy is what we call a deep copy operation, where I couldn't just copy the two data members, stored length and actual stir, of my string. I would need to go ahead and do something a little bit more intelligent. Give S2 its own character array that happens to have the same contents as S1. Because if I didn't do that, then my destructor would try to clean up the same array twice. I'd wind up with double deleting the same array, and that would be quite bad. That produces undefined behavior. So it's not just that this is a smart option here. It really is something that we generally need to do for a type like this. And the implementation of the copy constructor is pretty simple. It looks a lot like the other constructor, but it's simply copying from another myString object in this situation. And if we have a copy constructor, very often our class also needs a copy assignment operator. This is similar. Assignment and initialization are easy to get confused in C++ because they can both use the equals sign, for example, in certain situations. But the way to tell the difference is whether or not the target object already exists before you're writing to it. If you are using an assignment, happens when you are overwriting an object that might already have some previous value in it, something that already exists. And so in that situation, if I wanted to copy from S1 to S2, I would want the picture to look something like this. First, create a copy of the contents of S1 in dynamically allocated memory, and then give S2 control over that array and get rid of the previous array that it had contained, delete the old contents so that it's properly cleaned up. That's all just fairly simple copy operations. This is the kind of situation where you'd want to implement those copy operations yourself, generally speaking. But if I go ahead and just implement the copy operations like this, I've solved one problem. But in a sense, I create another, or I create an inefficiency, I should say, somewhere else. Because the myString class, like the studString class here, also has a plus operator that's designed to concatenate two strings together. So I want to be able to combine string S1 and string S2 when I create S3 by writing S1 plus S2, and I should get A, B, C, D, E, F as one combined string there. A perfectly reasonable thing to want to do. But as I've written my class here, myString just has the copy operations. If you write just the copy operations for a type like this, then the type really doesn't have move semantics. If you try to move from it, what you'll find is that it falls back to copying because you only wrote the copy operations for this type. And if that's what happens in this situation where we've got something like, where we're trying to create S3 from the strings S1 and S2, then, and again, this is assuming that the compiler doesn't elide the copy operation. More recent compilers probably would, depending on how you wrote that plus operator. But historically, part of the motivation for these move semantics, and I'll show you some other examples of where you might want to use this as well, would do something like this. The plus operator would create S1 plus S2. Here it's already done the work of assembling those two strings together. And then just the process of getting the value from S1 plus S2, that temporary object, into S3, the place where we really want it to be, would involve doing that same kind of deep copy if all we've got is the copy operations. And the thing is, that's basically pretty wasteful because we then immediately go ahead and destroy S1 plus S2. It was always meant to be a temporary object, but we meticulously went through this process of reproducing the exact string in S3 only to then destroy the original. And the idea behind move semantics is that that's not really the best way of doing things. It would be easier and faster if we did something like this, where we've already got a dynamically allocated array with the contents that we really want S3 to have. We can just hand off that array to S3. And then when we get rid of S1 plus S2, as long as we've done that handoff correctly, S3 now just owns that character array that originally belonged to S1 plus S2. And it should go ahead and do the cleanup when S3 is destroyed. But S1 plus S2 doesn't need to do anything. It can just hand off the character array to someone else. So that's the idea behind move semantics. But how do we make that work? Well, it comes down to what are called Lvalues and rvalues. So every expression in C++ is either an L value or an R value. Now these terms have been with C++ since, well, before it was C++, really. They go back to C. K and R introduced these terms in their original book, and they used the term L value in the sense that the term comes from an assignment expression like E1 equals E2 that we see here, where the thing on the left of the assignment has to be what we call an L-value expression. What makes there are certain properties that whatever expression appears on the left has to have in order for this assignment to be valid. Again, this is the original meaning of the term L-value. These terms have evolved a fair bit over time, but I think understanding where they come from is still quite helpful. So here, if I create an integer n, I can go ahead and assign 1 to n here. And that works specifically because n is not just an int, but because it's an L value of type int. Whereas 1 just is a simple literal. It's not an L value. There isn't a specific place in memory set aside where 1 always lives. 1 is what we call an R value, which is anything that is not an L value is an R value. And this can work with simple expressions like this, n and 1, but it also works with more complex expressions like x sub I plus 1 or the absolute value of p arrow value. Here, x sub I plus 1 is an L value. The square bracket operator, what it gives back is something that you can assign to in general. Whereas something like the absolute value function that simply returns back a value, that's going to be an R value. So most literals are R values, things like 3, 3.14159, the character literal A, those are all R values. Enumeration constants are also R values. So they're things that can only appear on the right side of an assignment. I can create objects of a type like the enumeration color here. And I could assign, if I created an object of type color, I could assign blue to that. But the symbolic name blue, that's an R value by itself. I can't overwrite it and change it to green, which, thank God, because you can only imagine the kinds of, what would it mean if we wrote the program to change the value of 10 into 0? The next time I write a 10, do I really want that to actually give me the value 0? Almost certainly not. We've already got an obfuscated C contest, and we can produce plenty complex programs that are confusing without being able to do things like this. So an L value, now I say it can appear on the left-hand side of an assignment. Really, an L value can appear on either side. An L value can be used as an R value. And in fact, the language refers to this as an L value to R value conversion. That's kind of a fancy way of saying that it reads the value out of the location where the L value, where the expression, the L value, is stored and gives it back to be stored somewhere else. When we are using something as an L value, we care about where it lives in memory because we're going to put a new value into that place that we can then get out later on. When we're using something as an R value, what we care about really is the value that it holds. What is currently stored there, or what does it evaluate to? All right. Now, this gets a little bit complicated. One of the ways in which these terms have evolved, a const object is a kind of object. And so if you have a const object, it is in fact an L value. It's just an L value that you can't assign to. This is one of the ways in which Kernighan and Ritchie's original definition broke down. It turns out that a const object is what we call a non-modifiable L value. Now, what's the difference between a non-modifiable L value and an R value? Well, a non-modifiable L value has an address. You can set up a pointer to point to it, like the pointer P here in this example. If I make max an object of type int, a const object of type int, I can take the address of max here, but min, which is here an enumeration constant, really is an R value. It doesn't have an address that I can take in this situation. So L values are both addressable and assignable. Non-modifiable L values are addressable, but not assignable. R values are neither, in general. Now, that gets a little bit more complex when we start talking about R values of class type, because temporary objects, like S1 plus S2 that we saw earlier, those things are R values. And we can get R values of class types in a few different ways. We can have a function call that returns a class object by value, or we can do something like use a function style cast to convert an object into a class type. So here, if I have this type T that has a constructor that takes an int and also a member function f that takes an int and returns an int, and then a non-member function g that takes an int and returns an object of type t by value, then any of these expressions here at the top, those will give me back a class R value, something of type t, that is an R value. And if I tried to take the address of any of those expressions, the compiler wouldn't let me. It would just stop me there. But you can actually apply a member function like that member function m to a class R value. I could write something like this, where I create an object of type t as essentially a temporary from the value 7, and then immediately call the f function on it and get back the result. And then that would be discarding the t object created from 7 at the end of that statement. It would just create it, call the member function on it, and throw it away. And f could even modify that object, because f is, if you go back and look here, it is a non-const member function. So it does have the ability to write to this thing. And if you think about it, this really does involve taking the address of that t object created from 7, because the way that a member function is implemented, it has a this pointer that's going to point to where that object lives in memory. In order to make that work, the compiler needs to effectively give the t object created from 7 a location in memory where it exists, at least for a little while. This is what's called a temporary materialization conversion. It takes something an R value that normally wouldn't have a location in memory where it's stored, that would normally just be something that's invented on the fly and immediately discarded, into this relatively short-lived object that does have a memory address. Again, it's a temporary object, so as soon as we've gotten back the return value of f, the temporary t object is going to be destroyed, but it does exist for at least a little while. So what we used to call references, and what a lot of people still call references in C++, if I'm being honest. If I hear someone say, I have a reference to an int, usually I'm assuming that what they mean is an L-value reference to an int, because that's the kind of reference that people are generally familiar with, and we tend to write more L-value references than R-value references anyway. So formally it's L-value references and R-value references, but a lot of people speak as if the terms were just reference and R-value reference. L-value references aren't any different from what we used to call just references. It's just a difference in terminology. So if I have, speaking here about a pointer rather than a reference, if I have a pointer to a T object, it has to point to an L value of type T, because it's pointing somewhere in memory. That object of type T has to be in memory in order for it to point to. That's at least conceptually, I say. The compiler may be able to optimize some of these things into cache, for example, depending on how you're using these pointers. But I'm speaking at a more conceptual level here about how things might work in general. And by the same token, an L value reference to a T has to bind to an L value of type T. I can't take, just like I can't take the address of 3 and set up a pointer to it, I can't bind a reference, an L value reference, to the literal 3 there. Both of these would be compile errors. And by the way, I would also get compile errors if I tried to point to or refer to an L value of the wrong type. It doesn't just have to be an L value, it has to be an L value of whatever type the pointer or reference is declared to refer to or to point to. Unless you're talking about an L value reference to const. There's a rule that says an L value reference to const T is allowed to bind to an expression that isn't an L value of type T. E can be an R value expression, and it can have a type other than T, as long as there's a conversion from whatever type T has, or E has, sorry, whatever type the expression has, into the type that the reference expects. This is another situation where the compiler performs one of these temporary materialization conversions. It places a temporary object of type T in memory, holding the converted value of the expression E here in memory, and binds the L value reference to that. So for example here, I can create a reference to a constant double and have it refer to the literal 1. And what will actually happen behind the scenes is that the 1 will be converted from an int into a double and then stored in some temporary location in memory for as long as this reference to const is going to exist. And then once that reference to const gets destroyed, once it reaches the end of its lifetime, the temporary object will be cleaned up as well. Now, again, this is conceptual. The compiler may very well be able to optimize these things away if it sees that I'm using, say, the literal 1 in this kind of situation. But if I'm working with more complex expressions that might be more difficult to optimize, then what I've just described is the general process. Now, the compiler doesn't invent a temporary like this unnecessarily. It'll go ahead, if you have an int and you try to bind a reference to const int to that thing, it'll bind the reference directly to that int object. It doesn't need to create a second temporary int in order to hold that copy. And in fact, again, the compiler may be able to optimize away RI entirely, depending on how we're using it. But but in general, it will just bind to the object directly. Now, we also now have rvalue references, which instead of the single ampersand operator, use the double ampersand operator. So here, this first line of code declares ri to be an rvalue reference to an int, bound to 10. And rvalue references are, well, we don't see them as often as we see other Lvalue reference types, but they can be used as function parameter types, return types, all the normal kinds of things that we can do with types in general. We can have rvalue references to const, but they're not really very interesting for reasons that we'll see. An rvalue reference has to bind to an rvalue. Even an rvalue reference to const will only bind to an rvalue. If I try to set it up so that to make one bind to an Lvalue, the compiler will reject that for me. Now, this is another situation where we get one of those temporary materialization conversions, the way that the compiler makes an expression like create ri as an rvalue reference of type int and bind it to 3 work is it places the 3 in a temporary location and binds ri to that temporary location. The difference is now we have a reference to non-const bound to that thing. So we could actually go ahead and modify the temporary object using that reference. If we're talking about just the literal 3, that's not particularly that interesting. We could have just used a regular int. But it becomes interesting when we're talking about more complex class types. So going back to our myString class, I could write another constructor for my myString type. I had a copy constructor that took a myString by reference to const, by Lvalue reference to const myString. Now I could write a second constructor that takes an rvalue reference to a myString. And this is how I give a type move-semantics in C++. Well, this is part of it. Now, I still have my plus operator that concatenates 2 strings together. But now when I go ahead to create another string, another myString from an existing myString object, the compiler chooses which constructor it's going to use depending on whether the argument being passed in, the source object, is an Lvalue or an rvalue. So creating S2 from S1 on the second line there, that still uses the copy constructor that I wrote before. But creating S3 from S1 plus S2, which was an rvalue object, that now uses the function that takes an rvalue reference, takes its argument by rvalue reference here. So the thing is, this gives us a way to identify when the source operand of something like this, like an assignment or a construction, an initialization, is a temporary object that's about to be destroyed, because an rvalue is one of those temporary objects. So when the compiler, ordinarily, the compiler would generate code for that assignment S1 equals S2 plus S3 as something like this. It would create a temporary myString object holding the value S2 plus S3. And then it would copy from that into S1 and then destroy the temporary. But that temporary value is something that it's going to be destroyed anyway. So, as I illustrated before, this is a situation where we could get away with taking some piece of the value from the right-hand side of the assignment and transferring it over to the left-hand side, essentially stealing it, if you want to prefer that language, moving it if you want to be a little bit more polite, less accusatory. That's a lot cheaper than making a deep copy of the right-hand side. And the R value, leaving it intact doesn't serve a lot of purpose because it's about to be destroyed anyway. So here, my move constructor for my string might look something like this. This is the constructor that takes an R value reference to a my string. And it goes ahead and creates the my string object here by copying, it takes the actual stir field, just copies over both fields, the actual stir field and the stored length field from the source object S here. And then it goes ahead and it sets the actual stir in the source object to point to null. That's important because the destructor for S, the thing that S is referring to, is still going to run. We haven't gotten to that point yet. This doesn't take the place of the destructor. It runs before the destructor. And when that destructor for the my string does run, it's going to try to delete whatever array it's currently holding, if it's still holding on to an array. By setting the actual stir in S to null putter here, we're making sure that S is no longer holding an array, a dynamically allocated array, so that delete statement is harmless. Deleting a null pointer has no effect. You don't need to check for null before you delete something. So that is a move constructor. And so our typical copy constructor takes an L value reference to const. A move constructor typically takes an R value reference to non-const, because the point of recognizing that it's an R value is recognizing that it's safe to destroy it. The object is about to go away anyway. So moving is sometimes called destructive copying. It's an optimization on copy operations that can be performed if we don't care about preserving the source operand, if we just need to get the value into a different location. Now, there's nothing special about R value references that let us do that. Interface-wise, they're the same as L value references. We could have theoretically written a move constructor, something that does the move operation, using a plain old L value reference. But if we did that, we probably wouldn't be happy with the results, because then we wouldn't actually be able to copy an object of type myString. What would look like a copy operation for most types would actually then be a move operation. So here, if I created one string S1 here, and then I tried to create a second object S2 from S1, this version of the constructor would let me do that, but in the process, S2 would effectively cannibalize S1. S1 would no longer be holding a string. So assuming that the output operator is written to recognize the null pointer, it would just write out nothing. In this situation here, when I write out S1, S2 is the only thing that would have any actual contents in it. For most types, we generally want to be able to copy them as well as move them. There are such things as move-only types, where we only want to be able to move them, but we still want to be forced to deliberately ask for that in general. We don't want to have the move take the place of the copy. Yeah. So hence, by implementing both a copy constructor and a move constructor for my string type, then the compiler will automatically use overload resolution to choose the move constructor only in the situations where the source operand is something that can be destroyed, where the object, the source is about to go away, so it doesn't matter if we destroy it in the process of creating the new object. Just like we can have a copy constructor and a copy assignment operator, a class can also have a move constructor and a move assignment operator. And the difference between the move constructor and the move assignment operator is the same as the difference between the copy constructor and the copy assignment operator, where the copy constructor is creating a whole new object where something didn't previously exist, whereas an assignment operator is overwriting an existing object. So generally speaking, we say a class has move semantics if it has both a move constructor and a move assignment operator. Generally speaking, if you write one, you want to write the other. It's very rare that you would want one but not the other. So almost always, if you declare one move operation, declare both. Now, for built-in types, things like integers and pointers, they don't have any special move semantics. If you try to move an int or a pointer, it just copies it. There's no advantage. In fact, to destroy the source operand when you're copying an int, you'd have to do extra work. You'd have to deliberately set the source int to something else in an extra operation. So move operations for built-in types and types that in general don't have these external resources like dynamically allocated memory, then copying is essentially the same thing as moving. Destructive move has no performance advantage for those types over a non-destructive copy. But for a type like string, implementing move semantics can have a noticeable performance benefit. So here, in this situation, I'm assigning from a temporary string object into S1 here. My move assignment operator might look something like this. This is a pretty simple example of how you could do that. Here I'm checking, the first line is checking for self-assignment. Odds are you wouldn't actually write something like A equals A, especially in a move situation. But there are ways that you could force it if you really tried, and it doesn't take a lot of effort to check to make sure we're not overwriting ourselves. So I generally think it's a good idea. But then here we go ahead and we destroy the old string that we were holding, and then copy over the data members from the S object. And again, we need to set the S object's actual stir so that it's now pointing to null, so that it doesn't try to clean it up after the assignment is over. Notice it returns an L value reference. Whatever you're assigning from, what you're assigning to should be an L value, because it's on the left-hand side of an assignment. That's traditionally what L value means. So, and since assignment operators typically return their left-hand operand, that thing's going to be an L value reference in general. This is a fairly simple move assignment operator here. If I were dealing with types that could throw exceptions on some of these operations, I might want to do something more intelligent. But here I'm taking advantage of the fact that I'm working with built-in types, pointers, and integers, where there's nothing in here that could potentially throw an exception. Right. Now, earlier I showed you the swap function. This was the C++ 03 swap function. from back at the beginning. If I try to apply this swap function to my string, it's still going to use copy semantics. The fact that I've added move semantics for my string doesn't actually change how this function works at the moment, because as far as the function is concerned, the source operand here, x, is an L value. So it's going to choose to do the copy constructor. X looks like the kind of thing, well, X is going to continue to exist on the next line here. We're about to overwrite it, but the compiler doesn't know that. And so the compiler is going to choose, if left to itself, to call the copy constructor in this situation. And the general rule is if something has a name, it's an L value. Only unnamed things can be rvalues. So both the creation of temp and the two assignment operations, all three of those are still going to select the copy version of the operation there. In order to steer the compiler in the direction of moving from the objects instead of copying from them, we use the std_move function. This tells the compiler that even though it wouldn't normally be safe to move from x, even though x is going to continue to exist, we're giving permission for the compiler to generate code that's going to move from x anyway. We don't care about preserving the value that's in x in this situation. In this case, because we're about to overwrite it. There's no need to preserve x's original value, because the very next thing we're going to do is replace that existing value. Now, so std_move will steer the compiler in the direction of using move semantics. If the type doesn't have move semantics, if I only have implemented copy operations on this thing, it'll just fall back to that. It won't. This code would still work. It would just use the copy operations instead. What std_move of x is really doing is it's returning x as an R value. You can think of it as just casting it into an R value reference, because the return value of a function doesn't have a name. It's taking something x that had a name and replacing it with something that's equivalent but doesn't have an official name. So calling std_move on x doesn't really move x by itself. It enables other parts of the code to move from x. If we had it to do over again, maybe we would call it something like make movable. Maybe not. You know, a lot of people like terse code, so std_move is what it was named. But yeah, it's a way of telling the compiler that it's safe to move from x, even in a situation where it might not normally be obvious that that would be the case. Now, what about inside a function that takes an R value reference? This is kind of weird. R value reference parameters, when you're in, although from outside the perspective of the f function, when the f function is called, the s reference here, the s R value reference, was bound to an R value. If I try to use s inside the function, it's treated as an L value, which, because it has a name, inside the context of the function, s is an L value. From the perspective of outside the function, s was the object that s was referring to was a short-lived temporary. But inside the function, it can continue to survive for several lines. So it actually needs to be treated as an L value in that case. If we wanted to move from s in this situation, we still need to actually go ahead and call std_move in this situation in order to explicitly move from s. And that should be the last use of s, because we have to assume that this is going to destroy the value that was in s at this point. All right. Now, There's a bit of an exception here, as there often is. Return expressions are, generally speaking, an exception to the previous rule. The operand of a return statement is implicitly movable if it's a function parameter or a local object. So in this function g here, where I am creating the myString temp internally to this function locally, and then populating it in some function-specific way that's obscured by the tildes. When I return temp, I can just write return temp as the result expression. And the compiler will consider moving from temp in this situation. It recognizes that this is the last place where I could possibly use temp. So it is okay to move from it at this point. Actually, saying it's implicitly movable doesn't really tell the whole story, because the compiler might actually be able to arrange it so that returning from G doesn't involve a copy or a move. This is the copy elision that I was talking about earlier. So here, suppose we have this code where the main function creates the string s by calling the function g. And so s is going to, the way that you would think of this as working on the surface, if you're not familiar with how it works behind the scenes, and the way it actually used to work before certain optimizations were made to the language, was s and temp would be separate objects. S exists inside main, temp exists inside G, and upon returning from G, the system would create S by moving, or if we're talking about a version of C++ that doesn't have move-semantics, copying from temp into the location that was set aside for S as part of main. But as of C++17, the compiler really treats it as if temp is an alias for S, effectively. The local object temp, the compiler recognizes where the return value of the function is going to go. And it effectively just places temp in the same location as S. If this happens, there isn't either a copy or a move involved in returning from G, because temp is already in the value is already in the location where it's supposed to be, the location of S in the calling function. So the object has just always been in the right place, and there's no need to move it. This notion, what I'm showing you here, is called named return value optimization. It's effectively storing a local value directly in the return value location, the place it will be placed, we think of it as being placed when we return from the function. And C++ has always allowed this. C++17 just made it mandatory. It was something that a lot of compilers already knew how to do, and it was something that was such a common technique that the language developers decided, there's no advantage to not doing this. Why don't we just say this is what always happens? So historically, it's called named return value optimization, but that optimization part isn't really true anymore because it's not an optimization. The compiler isn't taking a shortcut. This is just how the language works, how it's defined to operate. Now, in this situation, calling std move on an implicitly movable object can actually result in less efficient code. Here, if I actually go ahead and call std move in the return expression of G, that can actually make things less efficient, because that named return value optimization, well, as it suggests, it's for a named return value, something that has a name, which in this case, it previously was temp, but now the return expression is stood move of temp. So named return value optimization only works if it's naming a local object, if the return expression is specifically the name of a local object here. And by the way, function parameters don't count for this purpose. In a lot of respects, function parameters behave like local objects, but this is one situation in which that doesn't hold up, just due to the mechanics of how function parameters are passed around and how return values are handled. So in this case, by calling stood move, we've effectively taken away the name from temp. We're referring to it in a different way. And the compiler then has to fall back to using move construction, to placing the S that main is going to receive in a different place from where the local variable temp is located, and then moving from temp into that location. That covers everything that I wanted to say here. So, yep. Thank you very much for coming. I think we have a few minutes for questions. Yeah, try to use the mics if you can.
Hi, thank you for that talk. That was really good. Can you jump back to slide 65? I want to point something out.
Yeah.
So this is, recall the move assignment operator for the myString class.
Yeah.
And the thing I want to point out is the state of S, the argument, after this function is called on it. So notice that it depends on what the value of S is. If S happens to be equal to its target, then nothing happens. Both objects are unchanged.
Right.
Otherwise, stuff gets moved around and changed and deleted and whatever. So the point to note here is that after a move assignment or a move construction, S is in a valid but unspecified state. It's like memory has not been destroyed. Nothing's like, there's no undefined behavior, there's no memory leakage, whatever.
Right.
But now if you go back to slide 59, doing something like that where you're C-outing S1 after a move, that may result in undefined behavior in general. Like doing something, like after a move, an object should be either assigned to or pushed out of scope. Yeah,
this is not really a good thing. I mean, here I was trying to illustrate something that, the kind of a hole that you could fall into if you were to use, to make your copy operation, what we would normally call a copy operation. The phrases get kind of confused here because there's a temptation to want to call this a copy constructor anyway, because it uses an Lvalue reference when in fact it's really doing the behavior of a move. Yeah, I agree. In general, you do not want to, once you've moved from something, pretty much the next thing that should happen to that thing is it's either going to be overwritten or it's going to be destroyed. You typically can't rely on, you shouldn't make assumptions about what a moved from object, what state it's going to be in.
Thank you.
Yeah, thank you.
Thank you for the nice talk and the correct placement of constants. And could you please go to slide 77?
Yeah.
So this optimization here, or the non-optimization as in C++17, this is only possible if the function would be inlineable, or?
No, this should be, my understanding of the way that it works, roughly speaking, is that when the compiler generates the code for the function g, historically it would have created some space locally for holding the return value, and it would have filled in that return value inside the function within the return expression, and then it would have done something to copy or move that thing into the result. But instead, and I'm speaking kind of generally here, compilers over time got smart enough to realize that they could generate the code so that the return value location could be essentially specified by the caller. If the caller is going to receive the return value in some way, they have a location where it's going to go, and the code for the function can be generated so that it simply it uses offsets that refer back to the location where that thing would be in the calling context.
Okay, thank you. Yes, that makes sense.
That's oversimplifying a bit to some degree, but that is my understanding of how it works in general.
Okay. The other question I had, could you please go to slide 47?
Okay, we're running a little low on time here, so we may run out of time after this, but I'm happy to continue answering questions after we're done here. Yeah.
I know maybe one slide before. Yes. So this basically extends the lifetime of the temporary object I have on the right-hand side. So this constant reference I take there, right, could be a temporary object, so it basically extends the lifetime of that.
So here the 1 is an R value, what's formerly called a PR value.
Any R value could be a temporary, and then it would be extends the lifetime of that R value. We can discuss.
Yeah, it's a little bit complicated because you can, whatever temporary was created, when you have something that's being turned from an R value into a temporary object like this, it's the lifetime of the original reference, the first reference that's bound to, that really determines the lifetime of the temporary object. So if I create an L value reference to const that's based on another L value reference to const, you can form a chain like that where you can get into trouble. This is one of the common lifetime issues, or if you go to, there are a number of talks that have been given over the years about oddities in object lifetime.
Okay. So
that you can fall into here, but in general, it's the reference here. It's RD. It's the lifetime of RD that determines the lifetime of the temporary created from 1 here.
Okay.
Any other references that were referring to the same thing would be just kind of taking the lifetime as a given, and if that reference happened to outlast RD, then it could be referring to dead memory.
Okay, thanks.
Yeah. Right. I think we're out of time at this point, so thank you all for coming. I hope you enjoy the rest of the conference, and have a good trip back to wherever you came from.